You notice it more when the world is quiet. A glass of water trembling as someone closes a door, a curl of steam lifting off a cup of tea, a tiny ring of ripples spreading from a single raindrop. All the familiar things that feel perfectly understood until you look at them closely. Then, suddenly, the simple becomes mysterious. The ordinary grows strange, and you realize that the world is not made of explanations. It's made of questions disguised as everyday life. If you stand still long enough, you begin to see them. The places where physics loses its confidence, where reality hesitates, stutters, behaves in ways that textbooks don't entirely predict, not exotic phenomena from the edge of a black hole, but puzzles hiding right here, on kitchen counters and sidewalks, and the silent space between two heartbeats. There's something beautiful about that. Because the deeper physicists look into the universe, the more they discover that the greatest mysteries aren't always the distant ones. Sometimes the anomalies live in the warm, familiar glow of a lamp, in the dance of dust floating through a sunbeam, in the way a pot of water refuses to boil the moment you stare at it, as if the universe were shy. These everyday puzzles remind us that understanding isn't a permanent possession. It's temporary, conditional. We know things just well enough to function, but rarely well enough to relax. And nature enjoys slipping out of our grasp, especially when we think we've caught it. Before we sink deeper into this journey, if you enjoy wandering into the quiet weirdness of reality like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these slow voyages alive. When you think of anomalies in physics, you might imagine particle accelerators, cosmic explosions, equations scribbled across enormous chalkboards. But the truth is gentler, and somehow more charming. The universe breaks its own rules all the time, and most of the time you can find those cracks within arm's reach. Take water, the most ordinary substance you know. It pours, it freezes, it boils. You've known it your entire life. But water is one of the most physically bizarre materials in the universe. It expands when it freezes, unlike almost every other liquid. It can become supercooled, turning into ice instantly with a small disturbance. And under just the right conditions, hot water can freeze faster than cold, a puzzle that baffled everyone from Aristotle to modern engineers. Water, this simple everyday liquid, behaves like a secret agent pretending to be normal when it absolutely isn't. Heat isn't any more obedient. You experience it constantly, warm hands, cool air, sunlight on your skin, yet heat is not a thing moving from place to place. It's the collective motion of billions of particles doing an endless, chaotic dance. And the moment we try to describe that dance with perfect accuracy, physics falters, turbulence, the violent, swirling flow that appears when water pours from a faucet, remains one of the biggest unsolved problems in all of science. There are equations for it, of course, but they quickly explode into chaos, refusing to provide neat answers. Leonardo da Vinci sketched turbulent water 500 years ago, hoping to decode its pattern. He never succeeded. Neither have we. Even sound, something so familiar and comforting, holds secrets. The way voices echo in a room can be predicted. Sort of. But why certain frequencies resonate deeply in the chest, or why a whisper travels farther in a long hallway than a shout? Those are the little quirks that keep physicists up at night. Sound is simply vibrating air, yet sometimes it behaves like a steady wave, and sometimes like a mischievous creature darting between objects as if choosing its own path. We live inside these mysteries without noticing them, a pot lid rattling at a strange rhythm, a candle flame that flickers sideways without a breeze, a droplet of oil sitting perfectly round on water instead of mixing, a shadow behaving differently depending on the time of day. Every one of these has an explanation, yes, but the deeper explanation, the one that truly satisfies, often lies behind a curtain we don't yet know how to lift. Physics, despite its reputation for certainty, is an ongoing negotiation with a reality that keeps pushing back. And the closer we look, the more the anomalies multiply. You can see it in the history of science. Every major shift began with someone noticing something that shouldn't have happened. Mercury's strange orbit forced Einstein to reshape gravity. The colour of heated metal forced Planck to invent quantum theory. And even today, anomalies continue to act as little flashes of inspiration or mischief, guiding science forward. But this episode isn't about the distant cosmic ones. It's about the ones you can almost reach out and touch. The anomalies that sit beside you at breakfast. The ones that appear when you mix milk into coffee and watch the marbling swirl. The ones that hide in the hum of your refrigerator or the spark of static on a winter sweater. Reality is stranger than it appears. And the strangeness isn't waiting in deep space. It's right here, woven into the fabric of ordinary life. So take a breath. Notice the sound of the room around you. Maybe there's a faint vibration in the floor, or the gentle ticking of something cooling down. Maybe your drink has a tiny ring of motion you didn't see before. Or maybe the world feels completely still, which, in physics terms, is never true. Because even in the calmest moment, every atom is trembling, drifting, oscillating, changing. Stillness is just a misunderstanding we've agreed to accept. As we move deeper into this journey, we'll explore hot water that freezes faster than cold, droplets that levitate on cushions of vapour, bubbles that explode with flashes of blue-white light, and electrical materials that disobey every rule we've created for them. We'll step into storms, kitchens, laboratories, and even our own minds. Not as detectives trying to solve these anomalies, but as travellers observing them closely, gently, with curiosity rather than urgency. Because anomalies aren't mistakes, they're invitations, whispers from the universe saying, look again, things are not quite what you think. And the more you look, the stranger and more beautiful the world becomes. There's a moment, standing in front of a freezer, when the cold air spills out in a soft white breath, and you place a container of warm water inside. You close the door, the motor hums, the frost settles, and if you listen closely enough, you might hear a whisper from the past, a strange old rumour dating back more than 2,000 years. Aristotle mentioned it casually, almost like gossip from the natural world. He wrote that people sometimes noticed hot water freezing faster than cold. He didn't insist that it always happened. He simply observed it, puzzled by its inconsistency, as if nature occasionally performed a small trick just to keep us humble. Over the centuries, medieval scholars noted the same thing. Ice collectors in cold climates swore it was true. And then, sometime around the 20th century, science, armed with thermometers, equations, and growing confidence, politely dismissed the idea. Hot water freezing before cold water. Impossible. A misunderstanding. An illusion. As if Aristotle and generations of careful observers somehow weren't paying attention. But the universe, as it often does, waited patiently for the right moment to embarrass us. In 1963, in Tanzania, a secondary school student named Erasto Mpemba was making ice cream in a cooking class. To speed up the process, he placed a still warm mixture into a freezer, and to his surprise, and to the disbelief of his teacher, it froze faster than a cooler batch sitting beside it. Everyone told him he must have been mistaken. He insisted he wasn't. He kept repeating the experiment. It kept happening. Eventually, he approached a visiting physicist, Dennis Osborne, and asked him, with all the innocence and determination a curious student can carry, why this strange thing occurred. Osborne didn't have an answer, but instead of dismissing Mpemba, he chose the rare, humble path. He tested it, and the anomaly returned. Warmer water, under certain conditions, froze faster than colder water. It wasn't a myth. It wasn't a trick. It wasn't Aristotle being poetic. It was real. Sometimes. The key word is sometimes, and that single word is the reason physicists still don't fully understand the Mpemba effect, even today. If science loves anything, it loves reproducibility, the universe behaving the same way every time an experiment is performed. Predictability, symmetry, order. But the Mpemba effect is a mischievous guest who refuses to follow house rules. Some experiments show it clearly, others show the opposite. Some setups reveal a dramatic difference in freezing time, others show none at all. It behaves like water has moods, and in a way, it does. Several possible explanations rise and fall like waves, each offering a glimpse of truth without claiming the whole shoreline. Evaporation is the simplest one. Hot water loses mass more quickly as steam, so there's less of it left to freeze. Less water, faster freezing. A tidy explanation, but not universal. Many experiments show the effect even when evaporation is prevented. Then there's convection, the internal currents that swirl through warm water. Hot water circulates more vigorously, distributing heat more evenly. This can cause the upper layers to cool faster than expected, triggering earlier ice formation. It makes sense, until you find setups where convection should help the cold water just as much. Another explanation involves supercooling, one of water's strangest habits. Water doesn't always freeze at 0 degrees Celsius, 32 degrees Fahrenheit. Sometimes it slips below that temperature without forming ice at all, hovering in a delicate, unstable state. Cold water is more likely to supercool. As a result, it might stay liquid longer even when colder overall, while the hotter water cools rapidly and freezes immediately once it passes the critical point. This explanation is compelling, but again, not universal. Sometimes the cold water freezes normally without supercooling, and the anomaly still appears. There are explanations involving dissolved gases, noting that hot water releases them more quickly, which affects its freezing behavior. There are theories about hydrogen bonding, the microscopic stickiness of water molecules that changes with temperature. Some propose that the structure of water alters as it's heated, subtly but meaningfully, giving warm water a temporary personality shift that affects how it cools. Others point to thermal gradients, frost on freezer walls, container geometry, and even the microscopic roughness of the surface water touches. Every explanation solves part of the puzzle, none solve all of it. The Mpemba effect is less like a single phenomenon and more like a constellation of related behaviours, small interacting quirks that become visible only under the right conditions, like stars aligning. This is why, even in modern papers, you'll find phrases like, "The effect is real, but its precise mechanism remains elusive," and "We observe the Mpemba effect in some configurations but not others," and occasionally, "We have no idea why this happened." That's the charm of it. Water, the most familiar substance in your life, is also one of the most unpredictable. It expands as it freezes, a bizarre choice no other common liquid makes. Its solid form floats on its liquid form, another oddity that keeps oceans alive. It reaches maximum density not at its coldest point, but at 4 degrees Celsius, 39 degrees Fahrenheit. It self-organizes, breaks symmetry, forms fractal patterns, and stubbornly resists tidy explanations. In a way, water behaves like a living thing, not conscious but expressive. It hints at complexity we haven't fully mapped. It carries secrets in every ripple, every drop, every shifting bond between its molecules. And the Mpemba effect is one of its quiet performances, a reminder that even the simplest materials hold surprises. If you place 2 identical containers into the freezer tonight, one hot and one cold, the odds are good that nothing strange will happen. The cold one will freeze first. Everything will proceed exactly as expected, predictable, comforting. But under the right circumstances, with the right container, the right airflow, the right molecular arrangement, the right balance of motion and stillness, water might decide to surprise you. It might freeze faster simply because it can. And you'll stand there, freezer door open, cold air on your face, wondering for a moment if Aristotle was smiling somewhere. Because he noticed it, Mpemba noticed it. Countless quiet observers throughout history noticed it. A small, stubborn mystery tucked into ordinary life. A reminder that even after all our knowledge, understanding is never quite complete. In the deep cold of a freezer, in the quiet presence of warm water, the universe whispers one of its gentle rules. Nothing is as simple as it seems. Storms have a way of reminding us that nature is still in charge. The sky darkens, thunder rolls in long, heavy waves, and lightning slices through the clouds with a brightness that feels almost ancient. But every so often, after the familiar flash, something far stranger appears, something people have reported for centuries yet still can't fully explain. A sphere of light, roughly the size of a grapefruit or a small ball, floats into view and drifts as calmly as if it has somewhere to be. Throughout history, these glowing orbs have appeared in the most unexpected places. Sailors in the 1700s saw them skimming across wooden decks during storms at sea. Farmers in Europe reported them slipping quietly into barns, illuminating the air with a gentle glow before fading away. Families in old houses described bright spherical lights gliding through living rooms, sometimes passing directly through closed windows without leaving a mark. Pilots during World War II witnessed glowing spheres pacing their aircraft, guiding themselves through turbulent skies with movements that felt deliberate, almost curious. These sightings were so consistent that pilots gave them a name: Foo Fighters. They weren't enemy aircraft, and they weren't hallucinations. They were simply something unknown. For a long time, scientists didn't take these accounts seriously. Storms create confusion, they said. Lightning is blinding. Memory is unreliable. People exaggerate. The phenomenon became a kind of scientific folklore, interesting but not credible enough to investigate. Yet the reports never stopped, and more importantly, the descriptions from different centuries and cultures matched so closely that eventually physics had to pay attention, not because of superstition, but because the universe tends to repeat itself, and when thousands of people describe the same event the same way, something real is usually behind it. Ball lightning, as it came to be called, is typically described as a floating or hovering sphere of light, often white, yellow, or blue. It moves slowly and smoothly rather than flickering or rising like ordinary flames. It doesn't behave like a balloon, and it doesn't drift like a gas pocket. It simply travels through space with an unusual steadiness, sometimes changing direction without any obvious cause, and, perhaps most unsettling of all, it doesn't seem to require a source of fuel. It can last seconds before fading away or exploding with a sharp, startling sound. One of the most important turning points in the study of ball lightning came in 2012, when researchers in China were observing thunderstorms with high-speed cameras and spectrographic equipment. They set up their instruments, hoping to capture the chemistry of a lightning strike, and instead recorded something unexpected: a glowing sphere forming immediately after a bolt struck the ground. It floated horizontally across the field for more than a second before disappearing. The cameras and sensors didn't blink or imagine anything. They captured real data. The spectrum revealed vaporized elements from the soil, especially silicon, glowing and ionized in a structure resembling plasma. For the first time, science had physical evidence that matched centuries of eyewitness reports. But the mystery didn't end there. In laboratories around the world, researchers began accidentally creating similar luminous spheres. In some cases, electric arcs produced small, free-floating balls of glowing material that hovered briefly over surfaces. Some experiments with vaporized silicon produced moving orbs that looked remarkably like real ball lightning. Others created stable plasmoids that floated for seconds at a time. Yet none of these laboratory results perfectly replicated the natural phenomenon. They were close, very close, but always missing one key behavior. Some were too short-lived. Others didn't drift the way witnesses described. Some didn't produce sound or smell. Many lacked the eerie motion that seems almost intentional. Because of these differences, scientists still disagree on what ball lightning truly is. One of the leading explanations is that it is a plasma phenomenon, a self-contained, temporarily stable pocket of ionized gas held together by electromagnetic fields. This fits with some observations, but not with others, especially accounts of orbs passing through solid materials without damage. Another idea focuses on silicon nanoparticles created during a lightning strike. which burn slowly and produce a stable glowing sphere. It matches some of the spectrographic evidence from China, but again, not all events fit that pattern. Other theories invoke microwave cavities in the air, chemical reactions, quantum phenomena, or complex self-organizing systems that form spontaneously under extreme conditions. Each explanation covers part of the mystery, but none cover everything. And what makes ball lightning especially unusual is how personal the reports feel. People don't just see it from a distance. It often appears close enough to feel intimate. Some witnesses report it drifting near their faces before disappearing. Others describe it rolling along the ground or hovering over metal objects as if attracted by them. In rare cases, it has caused damage or injury, usually when it ends with a sudden explosion. There's a famous account from an 1800s church in Devon, England, where a glowing sphere entered during a storm, travelled down the aisle, and then burst violently, injuring several people. The description from that era mirrors modern reports almost perfectly. Despite centuries of sightings, modern instruments, and laboratory attempts, the phenomenon remains scientifically unresolved in 2025. It is one of the rare cases where the consistency of eyewitness accounts and the limitations of theoretical models collide. It's real. That much is almost certain now. But the exact mechanism behind its formation, stability, and disappearance is still unknown. Ask physicists today, and most will cautiously say the same thing. It's likely a plasma-related phenomenon, but we do not yet understand how it maintains its structure or why it behaves the way it does. And that is precisely why ball lightning remains one of the most fascinating everyday anomalies in physics. It's not a myth, but it's not fully explained. It's not supernatural, but it feels otherworldly. It's a phenomenon that reveals itself rarely, unpredictably, and briefly, just long enough to remind us that nature still holds secrets even in familiar places like stormy skies and quiet living rooms. Perhaps someday we'll understand how it forms, what sustains it, and why it behaves with such calm defiance of expected physics. But for now, it remains a strange, luminous wanderer inside thunderstorms, carrying with it the quiet reassurance that the world is still larger, still stranger, and still more mysterious than we think. If you pour a glass of water into a sink, you probably don't think of it as anything extraordinary. It's one of the most ordinary actions in the world. A quick motion, a small splash, a swirl of liquid disappearing down the drain. But in that single moment, you're witnessing one of the most difficult and least understood problems in all of physics. Every time water arcs from a tap and begins to churn and twist, it enters a regime that has defeated mathematicians, physicists, and engineers for more than a century. That simple swirl is called turbulence, and despite its everyday familiarity, it remains a genuine scientific mystery. Turbulence is the chaotic, swirling, unpredictable motion that appears when a fluid, water, air, even molten metal, begins to move with enough energy or speed. It shows up everywhere. The gusts of wind that knock umbrellas sideways, the rolling clouds before a storm, the foamy white water behind a boat, the spiralling flow inside airplane engines, and even the little eddies that curl around your feet when you walk along the edge of the sea. It is so common that you almost stop noticing it, until you realize that physics still cannot fully describe it. The problem begins with something called the Navier-Stokes equations. These are the fundamental mathematical rules that govern how fluids move. They were written down in the 1800s with the hope that they would unlock everything from weather prediction to ocean dynamics. And at first glance, they look simple. Just a few lines of math describing how velocity, pressure, and forces interact. But the moment a fluid becomes turbulent, these equations explode into complexity. They begin creating patterns so intricate and interconnected that even modern supercomputers struggle to predict what will happen next. This isn't an exaggeration. The Clay Mathematics Institute, the organization that offers million-dollar prizes for some of the hardest problems in existence, has a standing reward for anyone who can prove whether the Navier-Stokes equations will always produce smooth physical solutions or if they sometimes break down into mathematical chaos. The problem is so difficult that many of the world's top mathematicians won't even attempt it. And yet, that same impossible problem appears every time you watch rain swirling in a gutter or milk mixing into coffee. What makes turbulence so challenging is that it sits on the edge between order and disorder. If water flows slowly from a tap, it forms a clean, transparent stream. Everything is predictable. The molecules slide past each other in smooth layers. But as soon as the flow speeds up even slightly, the motion breaks. The layers collapse into spirals, swirls, and eddies. These swirls interact with one another, splitting apart, recombining, feeding energy downward into smaller and smaller structures. This cascade continues until the fluid is filled with spinning, unpredictable motion. Structures within structures, patterns inside patterns, like a fractal made from liquid motion. What's strange is how universal these patterns are. The swirls you see in a sink look remarkably similar to the giant cyclones found in Jupiter's atmosphere, airflow over mountains, currents in the Pacific Ocean, smoke rising from a candle, and even the plasma inside stars all exhibit turbulence with the same basic structure. The scales are different, some measured in millimeters, others in thousands of kilometers. But the mathematics is uncannily similar. Nature seems to use turbulence as a kind of universal language, repeating the same chaotic patterns at every size. Yet even with this consistency, predicting turbulence remains nearly impossible. Weather forecasting is a perfect example. Meteorologists can describe large systems very well, but the small turbulent movements of air accumulate, amplify, and eventually change the entire outcome. A tiny instability over the ocean today can evolve into a storm next week. The atmosphere is so full of turbulent motion that it becomes sensitive to the smallest disturbances. This is one reason forecasts grow less accurate as they stretch further into the future. It's not that the science is wrong, it's that turbulence multiplies small uncertainties until they dominate everything. Aircraft engineers face similar challenges. When designing wings, engines, and control surfaces, they must account for how air will behave as it rushes over every curve and angle. Smooth airflow is easy to calculate. Turbulent airflow is not. Engineers rely on extensive wind tunnel testing and enormous simulations to approximate what might happen. But even then, there are limits. The sudden, unexpected bumps you feel during a flight are not failures of technology. They are reminders that turbulence still obeys its own rules, not ours. In the oceans, turbulence controls how nutrients rise from deep water to the surface, how currents mix, and how energy moves across thousands of miles. Some of the most important climate processes on Earth depend on turbulence, yet they remain among the least predictable. Even climate models, sophisticated tools built on decades of data, struggle with the fine-scale, chaotic motions that transport heat through the ocean and atmosphere. And in your kitchen, turbulence reveals its strangeness in quieter, smaller ways. When water hits a pan at just the right angle, you see swirling spirals forming and collapsing in fractions of a second. When steam rises from a boiling pot, it begins smoothly and then suddenly breaks apart into chaotic motion. Even a simple cup of tea stirred with a spoon contains miniature versions of the same physics that challenge mathematicians working on billion-dollar supercomputers. Part of the mystery lies in how turbulence mixes the world together. Smooth flows keep layers separated, but turbulent flow blends everything into everything else. This mixing is incredibly efficient, almost unnaturally so. It's the reason perfume spreads quickly across a room and why smoke from a candle fills the air instead of rising in a thin column forever. The ability of turbulence to mix fluids is so powerful and so poorly understood that it remains one of the great open questions in fluid physics. And yet, despite all this complexity, turbulence feels familiar. It's one of the first things you ever touched. You felt it as a child running your hands through a stream or watching waves break on the beach. You see it in the shapes of clouds, the dust behind a passing car, the motion of leaves in the wind. It's something you experience constantly without ever recognizing how remarkable it is. The strangest thing of all is that the world we live in is mostly turbulent. Smooth, calm flow is the exception. Chaos is the norm. Rivers, storms, ocean currents, blood moving through arteries, air around buildings, even the motion of the Earth's molten core, all of it is turbulent. The entire planet is wrapped in a thin layer of constantly shifting, swirling air that refuses to follow simple rules. We live surrounded by chaos so ubiquitous that most of us never give it a second thought. Turbulence sits at the intersection of the familiar and the impenetrably complex. It is one of the most common experiences in nature, and yet we still lack a complete mathematical description of it. In a sense, turbulence reminds us that mystery doesn't always hide in grand or distant places. Sometimes it's right in front of you, twisting gently in the stream of water beneath your faucet. If you trace modern physics back to a single moment of confusion, a moment when the universe quietly revealed that it doesn't behave the way we think, it would be a small, almost innocent experiment involving a light source, a screen, and two narrow slits cut into a sheet of metal. It sounds like the kind of demonstration you might see at a science fair or in a dusty classroom. Nothing dramatic, nothing dangerous, just a beam of light passing through two openings. But when physicists first performed this experiment in the early 1800s, and again in more refined forms in the early 1900s, something deeply unsettling happened. Light did not behave like a collection of tiny particles, nor did it behave like ordinary waves. It behaved like both, depending on how it was observed. The experiment revealed an inconsistency at the heart of physical reality, a contradiction so fundamental that it forced science to rethink everything from energy to matter to the nature of knowledge itself. The strange part begins when light passes through the two slits. If it were made of simple particles, you'd expect it to form two bright bands on the screen, one behind each slit. If it were a wave, like ripples on a pond, the two waves would overlap, creating a pattern of bright and dark stripes called interference. But light does something more confusing. When not observed closely, it creates the interference pattern, as if it spreads out like a wave, touches both slits and then recombines. Yet if you place detectors at the slits to watch it more carefully, the pattern changes. The stripes disappear, replaced by two simple bands, as if the light suddenly decided to act like a particle going through one slit or the other. And the truly strange part is that this happens even when you send the photons one at a time. Each photon leaves the source, travels alone, and somehow still forms an interference pattern collectively with all the others, as if each individual photon knows whether both slits are open. The experiment seems to whisper that observation matters, that the universe behaves differently depending on how we choose to measure it, and that even the simplest beam of light carries some hidden information about its environment, something deeper than classical physics can explain. This strangeness isn't confined to laboratories. It quietly threads through your daily life, powering some of the devices you use without ever thinking about their microscopic drama. Take LEDs, for example. The small, bright lights that glow in your electronics, illuminate your house and colour your screens. They work because electrons must transition between energy levels, releasing discrete packets of light called photons. The very process depends on quantum rules, including the same wave-like interference that shows up in the double-slit experiment. It's embedded in the equations that allow electrons to occupy stable orbits, skip between them, and release energy in ways that make modern lighting possible. Microwave ovens are another example. They warm your food by using electromagnetic waves that bounce around the metal interior, producing standing wave patterns, essentially large-scale interference patterns. The reason the food heats unevenly is because these waves create zones of high and low intensity, exactly the way light creates bright and dark fringes in the double-slit setup. Without wave interference, microwaves wouldn't work at all. Even solar panels owe part of their efficiency to quantum behavior. Photons hit the panel and create electron-hole pairs, a process deeply rooted in the probabilistic nature of quantum mechanics. Understanding how light behaves at the smallest scale allows engineers to design materials that absorb energy more effectively. Every time sunlight powers a home, quantum interference plays a hidden role in making the process work. We don't notice any of this, of course. These technologies feel straightforward. They turn on, they glow, they heat, they power devices. But beneath the surface, the same puzzle that baffled physicists more than a century ago continues to operate quietly without ever explaining itself fully. Many scientists hoped that a concept called decoherence would answer the uncomfortable questions raised by the double-slit experiment. Decoherence describes the process by which quantum systems interact with their surroundings. The environment, air molecules, vibrations, thermal noise, disrupts delicate quantum states and forces them into classical, predictable behavior. It's the reason why macroscopic objects don't behave like waves. Decoherence offers a useful explanation for why interference patterns disappear when detectors are placed near the slits. Measuring the photons disturbs them, connecting them to the environment and destroying their coherent wave-like behavior. Decoherence is brilliant, powerful, and correct in many contexts, but it doesn't solve the weirdness. It explains how quantum states lose information, yet it never answers the deeper question. Why does observing the system collapse the possibilities into a single outcome? Why does measurement produce a definite result at all? Decoherence handles the loss of coherence, but not the existence of classical reality. It tells us how the pattern disappears, not why the photon seems to choose one slit or the other when we watch. Hidden inside this subtle distinction is the core mystery. The universe doesn't behave strangely because we interfere with it, but because its fundamental structure is probabilistic, not deterministic. The double-slit experiment reveals that nature behaves differently depending on which questions we ask. Not because it wants to hide from us, but because its underlying rules don't match our intuition. When we watch, the world becomes definite. When we look away, it behaves as a cloud of overlapping possibilities. The most fascinating part is how this strangeness is woven into objects all around you. Every time you unlock your phone with a fingerprint reader, the sensor relies on quantum tunneling, a phenomenon related to wave interference. Every time you plug in a flash drive, its memory cells rely on quantum electrons that behave like waves and particles. Even the computer or phone you're using to listen to this right now is possible only because quantum mechanics allows transistors to switch using microscopic effects originally discovered through experiments like the double slit. It's remarkable to think that the bizarre behavior of photons in a simple demonstration has shaped everything from lighting to communication to computing. The odd, wave-like nature of particles isn't a curiosity confined to laboratories. It's embedded in the everyday world, constantly active in the technology that fills modern life. The double-slit experiment doesn't just show that light behaves strangely. It shows that reality itself is built on foundations stranger than anything our senses can detect. The world feels solid, predictable, and continuous only because we observe it at a scale where quantum effects average out into familiarity. Beneath that surface, things do not behave the way they appear to. And sometimes, when we send a single photon through two tiny slits, the universe gives us a brief glimpse of how it truly works. There's a certain kind of headline that appears every few years, the kind that promises a revolution before the facts have settled. In the early 2000s, one of those headlines began to circulate in scientific forums, then in engineering circles, and eventually across mainstream news. A device called the EM drive, a strange conical chamber with no fuel, no exhaust, and no moving parts, appeared to produce thrust. Not much thrust, but enough to raise eyebrows, enough to challenge one of the most sacred rules of physics, the conservation of momentum. If the claims were true, The EM drive would break a rule considered as fundamental as gravity itself. It would accelerate without pushing against anything, without ejecting mass, without interacting with a medium. It would, in theory, allow spacecraft to move across the solar system using only electrical power, no propellant, no vast fuel tanks. And because the idea sounded a little like science fiction, a silent engine producing motion seemingly out of nothing, the story caught fire. The concept wasn't entirely new. In the early 2000s, British engineer Roger Scheuer proposed a resonant cavity thruster, a hollow, truncated cone in which microwaves bounce around, supposedly exerting a net force due to asymmetric radiation pressure. Most physicists dismissed it immediately. The idea appeared to violate Newton's third law, the principle that every action must have an equal and opposite reaction. If nothing is expelled from the engine, if no mass is pushed backward, how could the device move forward? Scheuer argued that the internal geometry of the cavity created an imbalance in electromagnetic fields that would result in a net thrust. Critics countered with a simple question: where does the momentum go? Scheuer insisted he had test results showing tiny but measurable thrust. Most assumed he was measuring noise, vibration, or thermal expansion, not a real physical effect. But then something unexpected happened. A laboratory inside NASA, known as EagleWorks, decided to test it. NASA EagleWorks was a small, somewhat experimental group within Johnson Space Center, tasked with exploring advanced propulsion ideas. They weren't in the business of validating fringe devices, but the cost to test the EM drive was low, and the claims were gaining attention. So Dr. Harold "Sonny" White and his team set up a vacuum chamber, assembled their own version of the drive, and began running experiments carefully shielded from external interference. In 2016, after years of cautious work, EagleWorks published a peer-reviewed paper stating that their tests had detected a tiny but statistically significant thrust. The magnitude was extremely small, on the order of tens of micronewtons, but it was above the noise threshold. For a moment, the scientific world trembled. If NASA was reporting a positive result, perhaps Scheuer had been right all along. Engineers began sketching designs for propellantless satellites. Journalists wrote about the possibility of reactionless drives. Forums filled with speculation, skepticism, and excitement. But the story didn't end there. As soon as the EagleWorks paper appeared, laboratories around the world began replication attempts. Some were informal groups of engineers and enthusiasts. Others were academic labs with more controlled environments. At first, a few reported faint signals, enough to keep the conversation alive, but as the experiments became more refined, as temperature changes were controlled more tightly, as mechanical vibrations were reduced, and as magnetic fields were isolated, something became clear. The signals were not consistent. Several teams discovered subtle thermal effects. The device heated slightly during operation, causing tiny shifts in equipment that were easily mistaken for thrust. Others identified electromagnetic interactions with the test stands themselves. Once compensation was applied, the apparent thrust dropped to zero. One of the most definitive tests came from a German group at the Technical University of Dresden. They evaluated multiple EM drive configurations, shielded them meticulously from interference, and found no thrust at all. The earlier signals evaporated under stricter controls. By 2021, most physicists concluded that the EM drive did not produce thrust. The effect was likely experimental error, thermal expansion, vibration, or electromagnetic coupling disguised as movement. And yet, despite this conclusion, the EM drive controversy remains a fascinating piece of scientific history, not because it worked, but because of what the journey revealed about the scientific process. Even debunked anomalies matter. They remind us that science is not a static list of truths, but a method, a cycle of curiosity, testing, refinement, and correction. A claim that challenges foundational laws deserves scrutiny. not ridicule. It must be tested honestly, rigorously, and repeatedly. The EM drive earned attention not because it was plausible, but because the consequences of it being real were enormous. The potential was too transformative to ignore, and the cost to investigate was small compared to the knowledge gained. In a way, the EM drive controversy teaches an important lesson about scientific imagination. Some of the most groundbreaking technologies in history were once dismissed as impossible flight. Lasers, semiconductors, quantum mechanics itself. Being open to new ideas, even wild ones, is essential. But so is the discipline to examine those ideas critically without becoming attached to them. The EM drive also highlights the value of experimental rigor when researchers isolated thermal noise, vibration, electromagnetic interference, and other variables. They were not trying to disprove anything, they were trying to uncover the truth. The fact that replication failed is not a defeat, it is a success of the scientific method. It shows that our understanding of physics remains intact, and that the rules governing momentum and energy still hold. But there's more to it. The EM drive captured the public imagination because it spoke to a deeper desire, the hope that the universe may still harbour loopholes, shortcuts, or surprises, even when an anomaly disappears under scrutiny. The curiosity that led us to test it is meaningful. It keeps science exploratory. It keeps questions alive, and it keeps us humble enough to revisit old assumptions when new data appears. Today, the EM drive is generally regarded as a resolved anomaly, not a real one, but an instructive detour. Yet it remains an example of how science works at its best. Open-minded but rigorous, imaginative but grounded, willing to investigate ideas that challenge our understanding, but unwilling to accept them without evidence. And it reminds us that even when the answer is no, the process of asking is what pushes us forward, and the universe may not grant us reactionless propulsion, but the search for it strengthened the way we test, verify, and explore. And in that sense, the EM drive did exactly what anomalies, real or imagined, are meant to do. Spark curiosity, sharpen our tools, and encourage us to look at familiar laws with fresh eyes. Superconductivity has always felt like one of nature's quiet magic tricks, a behaviour so strange, so unlike anything in everyday life that it still surprises physicists more than a century after its discovery. At its heart, superconductivity is simply this. A material suddenly forgets how to resist. Normally, when electricity flows through a wire, electrons bump into atoms, lose energy, and produce heat. That is why phone chargers warm up, why light bulbs get hot, and why no conductor is perfect. But in a superconductor, all that chaos stops. Below a certain temperature, resistance drops to zero. Not almost zero, not very small, but exactly zero electric current can circulate indefinitely, losing no energy whatsoever. If you start a current in a superconducting loop and leave it alone, it will keep flowing for years, centuries. In principle, even for the age of the universe, it's as if the electrons suddenly enter a trance, moving with perfect coordination through a crystal lattice that no longer pushes back. The everyday analogy would be traffic on a highway. Under normal conditions, cars slow down, interact, jam, stop, accelerate. But in a superconductor, it's as if every car on the road somehow locks into a synchronized pattern, all moving at the same speed, never colliding, never braking, never losing momentum. The friction of normal life disappears. A perfect flow emerges. To achieve this, materials typically must be cooled to extreme temperatures. Early superconductors needed to be cooled close to absolute zero, around minus 273 degrees Celsius, minus 459 degrees Fahrenheit. Later discoveries pushed the threshold higher to around minus 196 degrees Celsius, minus 321 degrees Fahrenheit, the temperature of liquid nitrogen. These were celebrated as high-temperature superconductors, even though they were still unimaginably cold by everyday standards. The term high temperature simply meant less impossible, but the dream, whispered for decades, has always been room temperature superconductivity. A material that works at 20 degrees Celsius 68 degrees Fahrenheit, or even 0 degrees Celsius, 32 degrees Fahrenheit, without requiring exotic cooling. Such a discovery would reshape technology overnight. Power grids could transmit electricity without loss. Magnetic levitation could become common medical imaging, computing, transportation, energy storage, all transformed. For years, the search moved slowly. Then, in 2023, a paper appeared online from a small team in South Korea. They claimed they had discovered a material, LK99, a modified lead apatite compound, that became superconducting at room temperature and normal pressure. Not only that, in a demonstration video, a tiny piece of the material tilted and partially levitated above a magnet, wobbling in place. It was not perfect levitation, but it looked like the signature behavior of a superconductor, the Meissner effect, which expels magnetic fields. Within days, the story exploded. Laboratories around the world raced to replicate the synthesis. The internet treated LK99 like a global treasure hunt. Researchers posted real-time updates, photos of their samples, resistance measurements, and videos of tiny pellets bouncing around on magnets. People who had never heard of superconductors suddenly knew the name LK99 and debated its structure, doping levels, and crystal phases. It became one of the first true viral physics phenomena, spreading with the speed of a cultural event rather than a scientific discovery. For a moment, a brief, electrifying moment, it felt as if we were witnessing history, the kind that changes textbooks, industries, and economies. But as replication attempts grew more rigorous, the excitement faltered. Most labs found that their samples did not superconduct. The levitation effect, when present, was often just partial ferromagnetism, the same phenomenon that lets a refrigerator magnet stick to metal. Some samples cracked, others behaved inconsistently, and none produced the unmistakable signature of zero electrical resistance. It turned out that LK99 likely exhibited small impurities of copper sulfide, a known semiconductor that undergoes a magnetic transition around room temperature. The levitation, the strange signals, the excitement, many of these could be explained by mundane effects. Eventually, more controlled experiments showed no superconducting behavior. The anomaly faded. But the LK99 story remains important because it revealed something deeper about the scientific process. It highlighted how fragile extraordinary claims can be and how quickly they unravel when subjected to strict measurement. It also revealed how strongly humanity wants breakthroughs, how ready we are to imagine a future where electricity flows without loss and materials carry currents with perfect grace. Even though LK99 fell apart under scrutiny, the curiosity and energy it generated were genuine. For a brief moment, the world remembered that physics can still surprise us. And in truth, the dream of room temperature superconductivity hasn't been abandoned. It's simply more complicated than social media headlines suggest. Real high-temperature superconductors exist, and they continue to puzzle physicists. Many of them are copper-based ceramics, known as cuprets, discovered in the 1980s. They superconduct at temperatures as high as minus 135 degrees Celsius, minus 211 degrees Fahrenheit, which is astonishing compared to earlier materials, but still very cold. Others are iron-based compounds discovered in the 2000s, with similarly high but sub-zero critical temperatures. The most striking breakthroughs in recent years came from experiments using extreme pressures, millions of atmospheres, to create superconductivity at temperatures as high as 15 degrees Celsius, 59 degrees Fahrenheit. But those pressures are so intense that the materials cannot exist outside specialized laboratory conditions. They behave more like exotic phases of matter than practical technologies. What makes these materials so strange is that their mechanisms remain partly unexplained. Traditional superconductors work through a process known as Cooper pairing. Electrons bind into pairs that move through a lattice without resistance. But high-temperature superconductors do not follow this simple rule. Their electrons interact strongly, unpredictably, and in ways that break many assumptions about how solids behave. Even today, the underlying physics is not fully understood. Scientists can observe the behavior, but not fully explain it. Predictions often fail. Experiments produce surprises. This means that the path to room temperature superconductivity is not a straight line. It's a landscape of unknowns, a territory where the rules of electricity begin to blur, where materials behave in ways that defy intuition, and where electrons move with a collective intelligence that still feels mysterious. The LK99 episode, in a way, was a reminder of that mystery. Not a breakthrough, but a momentary opening in our collective imagination, a sign of how ready we are to believe that nature might still grant us a shortcut, and perhaps, in time, it will. If high-temperature superconductors still defy complete understanding, then the possibility remains open, not through viral hype, but through persistent research. Superconductivity continues to be one of the most unusual states of matter we've ever discovered. It looks ordinary from the outside, just a quiet piece of solid material, but on the inside, electrons move with a harmony that feels almost sculpted. At absolute zero, at liquid nitrogen temperatures, at extreme pressures, and perhaps someday at room temperature, matter can shift into a state where resistance simply disappears. It is one of the clearest reminders that what we see at the human scale is only a small fraction of how matter truly behaves. And even though LK99 did not rewrite physics, it succeeded in something else. It reminded the world that mystery still lives inside the materials we hold in our hands. One day, maybe years from now, or decades from now, the real room temperature superconductor may appear, quietly at first, then unmistakably, and when it does, it will change more than just technology. It will change how we understand the hidden choreography of electrons and the surprising ways matter can choose to behave. If you ask a physicist what makes the universe predictable, they'll tell you it begins with measurement, observing a system, defining its initial conditions, and trusting that the laws of nature will do the rest. But there is one place in science where measurement becomes tangled with belief, where expectations change outcomes, and where the boundary between the observer and the observed begins to blur. It doesn't happen in particle accelerators or deep space telescopes, but inside the human body, in the quiet space where the mind meets biology. This is the placebo effect, an anomaly so widely documented and so persistent that it has become one of the strangest intersections of physics, biology, psychology, and consciousness. In simple terms, the placebo effect describes the actual, measurable improvement caused not by a drug or treatment, but by the expectation of improvement. You take a sugar pill believing it will reduce pain, and your body responds as though you had taken a real analgesic. You breathe easier, your heart rate lowers, your immune response strengthens, your symptoms decrease, not because of chemistry, but because of belief. It sounds like a trick of the mind, but it shows up in measurable physical changes. Researchers have scanned the brains of patients before and after taking placebos and watched as neural activity in pain-processing regions decreases, endorphins increase, inflammation markers fall, and even immune cells behave differently. In some cases, the body produces the same physiological response as it would to a real medication. This is where the anomaly begins. Physics is built on cause and effect. Biological systems follow chemical pathways. Yet, in placebo responses, expectation alone, something intangible, triggers measurable biological effects. The mind, which physics usually treats as a passive byproduct of matter, suddenly begins acting like an active participant. For decades, scientists believed that the placebo effect relied on deception. The idea was simple. If people believed they were receiving a treatment, their bodies responded accordingly. But in recent years, this assumption has been overturned by a series of remarkable studies from Harvard Medical School. In these trials, patients were given open-label placebos, meaning they were told openly, without any ambiguity, that the pills contained no active ingredient. The bottle was clearly labelled as a placebo. The participants were told exactly what they were taking, and yet many of them improved anyway. In studies involving chronic pain, irritable bowel syndrome, migraines, and even some forms of depression, patients who knowingly took placebos reported significant symptom relief. Their bodies responded even though their conscious minds knew the pill contained nothing. It was not the belief in the pill that mattered, it was something deeper, perhaps the ritual of treatment, the context, the expectation that the body might respond, or the subtle subconscious pathways shaped by trust and attention. This discovery forced scientists to rethink what the placebo effect really is. It isn't just a trick, it's a biological response mechanism tied to perception, meaning, emotion, memory, and expectation. The brain, recognizing the structure of a healing ritual, activates systems that modulate pain, regulate hormones, and alter immune responses. In other words, belief doesn't just make you feel better, it changes the physical state of your body. Pain, for example, is a complex blend of sensory input and perception. Placebos can reduce pain by activating endogenous opioids, chemicals the body naturally produces to dull discomfort. Imaging studies show that placebo treatments alter activity in the prefrontal cortex, the anterior cingulate cortex, and the periaqueductal gray, regions associated with attention, interpretation, and pain modulation. In some cases, the brain produces a pain-relieving response nearly as strong as medical analgesics. The immune system shows similar behavior. In a now classic study, volunteers were given a drug that suppressed immune function while also being exposed to a specific taste. Later, they were given only the taste, no drug, and their immune systems responded as if they had taken the medication. Conditioning, expectation, and ritual combined to trigger an immune response without any chemical cause. The mind reached into the body and adjusted the machinery. This is why the placebo effect is a biological physics anomaly. Physics is designed to model systems without reference to intention, expectation, or subjective experience. But in humans, and possibly in other animals, observation does not just measure a system, it becomes part of it. The observer is not outside the equation. The observer changes the equation. In quantum mechanics, the act of measurement alters the state of a particle. In placebo research, the act of measurement, attention, expectation, interpretation alters the state of the body. These parallels are not superficial metaphors. They reflect a deeper issue. Physics does not have a complete model for consciousness, yet consciousness clearly has the ability to affect physical systems in ways that are measurable and reliable. The anomaly becomes even more pronounced when you consider that placebos can create both positive and negative effects. The nocebo effect, the dark sibling of the placebo, occurs when expectation of harm creates real symptoms. If a patient believes a harmless substance will cause nausea, dizziness, or pain, the body may produce exactly those sensations. The nervous system responds to meaning, not chemistry. This suggests that the body is constantly reading context, interpreting signals, and adjusting itself in ways that blur the line between physical and experiential. The boundary between mind and matter becomes porous. The placebo effect is not magic, but it reveals something important. The body is not a passive machine. It listens, reacts, adapts, and sometimes obeys expectations, even when those expectations contradict physical inputs. Physics struggles with this because its equations do not include subjective experience as a variable. There is no symbol for belief, no operator for expectation. But biology seems to require them. Consciousness is not just a spectator, it is a participant in the system. The placebo effect is one of the clearest windows into this entanglement, a reminder that the observer cannot always be separated from the observed. This brings us to a deeper question, one that extends beyond clinics and laboratories. If belief can alter physiology, and if attention can change the body's internal state, then perhaps consciousness plays a more active role in physical processes than we usually acknowledge. Not in a supernatural sense, but in a way that reflects how deeply intertwined mental and physical systems are. The placebo effect is a gateway, not to pseudoscience, but to a richer understanding of how mind and matter interact. It invites us to reconsider the nature of observation, the power of expectation, and the complexity of living systems. It blurs the boundaries between disciplines and reminds us that some of the strangest anomalies are not found in space or quantum laboratories, but inside our own biology, and it suggests something quietly profound. The mind is not just a passenger in the body, it is one of its instruments, capable of tuning, adjusting, and sometimes healing, not through chemistry or force, but through meaning. If you've ever stood on a road at night and watched a pair of distant headlights appear through fog, you may have noticed that the light often looks warmer, sometimes yellow, sometimes almost orange, compared to the same lights when a car is nearby. Sunsets do something similar. The sun begins the day with a cold, white brightness and ends it with deep golds, reds, and purples. It feels like the light itself is getting tired, as if distance and effort soften its energy. This impression is so common that early astronomers once believed it happened in space as well. That light travelling across the universe simply lost energy with distance, weakening into red the farther it went. That idea, tired light, is now known to be wrong in the cosmic sense. But on Earth, in your daily experience, something very similar does happen. Distant lights look redder and dimmer, not because they lose energy in the way early cosmologists imagined, but because of the intricate way light interacts with the atmosphere, and because of the equally intricate way your brain interprets what you see. The first piece of the puzzle is Rayleigh scattering, one of the most elegant and far-reaching concepts in optical physics. Rayleigh scattering explains why the sky is blue, why sunsets are red, why distant mountains look hazy, and even why fog turns car headlights into soft, warm halos. It comes down to the size of the particles in the air. When light moves through the atmosphere, it encounters molecules of nitrogen and oxygen much smaller than the wavelength of visible light. These tiny particles scatter shorter wavelengths, blues and violets, far more effectively than longer wavelengths like red and orange. This selective scattering means that as sunlight passes through a thicker slice of atmosphere near the horizon, more of the blue light is diverted away, leaving the reds and oranges dominant. The sun isn't changing colour. The path the light travels is. The atmosphere filters the day gradually, the way stained glass filters the light inside a quiet cathedral. The same process happens on a smaller scale when you look through fog, mist, or even dusty air. The particles scatter blue wavelengths first, softening the overall colour and leaving behind warmer tones. That's why distant headlights seem yellowish in poor visibility. The blue component fades before it reaches your eyes. The effect isn't as dramatic as a sunset, but it follows the same logic. Light losing its higher energy components through scattering, not losing energy itself. There's another subtle effect at play, me-scattering, which occurs when the particles in the air are closer in size to the wavelength of the light. Fog droplets, for example, are much larger than atmospheric molecules. Me-scattering doesn't discriminate as strongly between colours, it scatters all wavelengths more evenly, but combined with Rayleigh scattering, it changes the brightness and contrast of distant lights in ways that can make them appear warmer or dimmer, especially when surrounded by diffuse glow. And hovering above these physical processes is something even more interesting, the way the human brain interprets distance, brightness, and colour. Our visual system evolved to interpret light in the context of objects and environments, not as pure physical signals. When we see a light source through mist, haze, or long atmospheric paths, The brain interprets the decrease in brightness as distance, but it also interprets the change in colour temperature as a cue. In natural environments, warm colours often accompany low illumination, such as firelight, dawn, or dusk. Our brains unconsciously associate warmth with fading light, so when physical scattering subtly alters the light, the mind completes the pattern, tinting the scene with emotional and perceptual assumptions drawn from experience. This means that distant lights look redder for two reasons. Physics removes the bluest wavelengths, and the brain interprets the softened, dimmer signal through a lens of expectation. The result is a perceptual anomaly, rooted in the hard mathematics of wave scattering and the soft architecture of human perception. The illusion becomes even more clear if you compare photographs with your own eyes. A camera records the light that reaches it without interpretation. It doesn't brighten shadows unless instructed. It doesn't adjust white balance unless told. But your brain adjusts continuously, balancing contrast, compensating for glare, enhancing edges, and interpreting colours based on context. In scenes where redder light appears at a distance, especially in fog or low sun, the brain exaggerates the warming effect because it treats colour as a storyteller rather than a measurement. It's trying to give you an impression of the environment, not a spectrometer reading. This is why sunsets feel so emotional. The physical explanation is straightforward. Sunlight travelling through a long, dense path of atmosphere loses its blue wavelengths through Rayleigh scattering, leaving the longer reds and oranges. But the beauty you perceive is shaped by the mind as much as by the sky. Your brain reads the lowering sun as a transition, the end of a cycle, and brings meaning to the colour shift. The physics shapes the palette. The mind paints the mood. The tired light illusion in everyday life reveals how easily our senses blend objective physics with subjective interpretation. Light travelling through fog doesn't actually grow weaker in the sense early astronomers imagined. It simply becomes filtered by the air, but the impression of tiredness, the sense of distance, fading, dimming, warming, is created by your perceptual apparatus, which evolved not to measure wavelengths, but to read the world in terms of survival, emotion, and pattern. It's a reminder that the world we see is not the world as it is, but the world as interpreted by a nervous system shaped by long histories of adaptation. Light changes with distance because atmosphere changes it, and because our perception rewrites the information in a way that feels natural, even inevitable. This blend of physics and perception is everywhere. Distant streetlights on a cold morning glow warmer because the air filters them. Distant mountains appear blue because scattering sends more short wavelength light into the line of sight. The moon looks larger near the horizon because your brain compares it to earthly objects. These are physical signals shaped by cognitive expectations, creating illusions that feel as real as the laws that govern them. The tired light illusion doesn't reveal a failing in vision or understanding. Instead, it highlights a deeper truth. Even simple sensations result from intricate collaborations between the physical world and the mind that perceives it. Fog, molecules, scattering, distance, brightness, colour, expectation, all combine to create what you see. And it suggests something quietly profound. In the space between photons leaving a distant source and the moment they arrive in your consciousness, an entire universe of interpretation takes place. The world you perceive is shaped by physics, but it is completed by you. There are moments in physics when the universe behaves in a way that feels more like a riddle than a rule. And quantum tunneling is one of those moments. Imagine a small hill, not large, not steep, just tall enough that a rolling ball doesn't have the energy to climb over it. In the everyday world, the conclusion is simple. The ball stops, the barrier wins. But at the quantum scale, matter doesn't follow this logic. Instead, electrons can appear on the other side of an energy barrier instantly without crossing it in any classical sense. It looks as though they materialize through the wall rather than going over it. slipping through a forbidden region as if the rules were momentarily optional. This phenomenon is called quantum tunneling, and despite being one of the most counterintuitive behaviors in nature, it is also one of the most common without it. The sun wouldn't shine, electronics wouldn't work, and chemistry itself would look completely different. It is an anomaly so powerful and so embedded in the world that we rarely notice how strange it really is. The idea of tunneling comes from the wave-like nature of matter. According to quantum mechanics, electrons aren't tiny spheres orbiting nuclei. They exist as probability waves that spread out across space. These waves can leak into regions that classical physics would forbid, regions where the electron shouldn't have enough energy to exist. If the wave extends far enough, there is a small but real chance that the electron will be found on the other side of a barrier, no climbing, no impact, no breaking through. Just an abrupt relocation. For decades, physicists debated a deceptively simple question. How long does tunneling take? When an electron appears on the far side of a barrier, did it spend time inside the barrier? Did it travel through it at some finite speed? Or is tunneling an instantaneous event, something that sidesteps the usual constraints of time altogether? For much of the 20th century, this question remained philosophical because there was no way to measure tunneling on the tiny timescales involved. But in recent years, ultra-fast lasers have given researchers the tools to probe these events with extraordinary precision. Some lasers operate on the scale of attoseconds, quadrillionths of a second, short enough to watch electrons move, jump, scatter, or rearrange themselves around atoms. Using these attosecond laser pulses, physicists have been able to measure tunneling delays more directly than ever before. The results have been surprising and controversial. In some experiments, electrons appear to tunnel with no measurable delay, effectively instantaneously. In others, the delay is incredibly small, so tiny that it challenges our usual understanding of speed and motion. At first glance, it seems as though the electron could be moving faster than light inside the barrier, but that interpretation breaks the rules, so researchers had to rethink how tunneling actually works. The emerging understanding is subtle. When an electron tunnels, it doesn't travel through the barrier the way a particle would move through space. Instead, the electron's probability wave penetrates the barrier. The moment the wave appears on the far side with a high enough probability, the electron can be detected there. The whole process doesn't involve a classical trajectory, so questions like how fast was it going don't apply in the usual sense. The electron isn't violating relativity because it isn't moving through the barrier at all. It is re-emerging according to quantum rules that don't resemble motion in space. This still feels unsettling. Even physicists admit that quantum tunneling doesn't align with classical intuition, and that measuring tunneling time may require us to redefine what time means at the quantum scale. The ordinary world has clocks and distances and speeds. The quantum world has probabilities, amplitudes, and uncertainties. Tunneling lives in the space between those two descriptions, making it one of the most difficult and fascinating anomalies in modern physics. What makes tunneling even more interesting is how often it appears in everyday technology. Every time you use a flash memory drive, whether it's a USB stick or the storage in your phone, you are relying on quantum tunneling flash memory works. By trapping electrons in tiny regions inside a semiconductor, writing data involves using an electric field to make electrons tunnel through a thin insulating barrier. They don't go over it. They don't melt through it. They tunnel. Your photos, messages, and apps exist because electrons perform tiny quantum escapes inside the storage medium. CPUs use tunneling too. As transistors shrink to nanometer scales, the thin barriers that keep electrons separated begin to allow tunneling to occur more easily. Engineers have to design around these effects because at such small distances, electrons don't respect human expectations. They appear where they shouldn't be, slip into places that were meant to block them, and complicate the orderly flow of information. At the cutting edge of microprocessor design, tunneling is both an obstacle and a tool. Even LEDs and laser diodes rely on quantum tunneling in their operation. Electrons cross potential barriers inside semiconductor junctions to release photons, the same particles that illuminate your room or your screen. This means that every modern electronic device, every phone, every laptop, every router, includes components where tunneling is not a rare anomaly, but a central feature. And yet, underneath all this practicality, the strangeness remains. When the electron appears on the other side of a barrier without crossing it, the event doesn't fit neatly into classical language. We can describe the mathematics precisely. We can measure the timing with attosecond accuracy. We can build devices that depend on tunneling by the billions. But we still cannot tell a simple classical story about what the electron did. The event is not fully visualizable. It resists metaphor. Perhaps that is what makes quantum tunneling so captivating. It is not just a curiosity of particle physics, it is a reminder that the rules of the microscopic world operate beneath the surface of our everyday experience, quietly setting the stage for technologies that define modern life. It tells us that matter is more fluid, more probabilistic, and more interconnected than it appears, that electrons don't always move the way we imagine, and that some processes happen not by crossing distances, but by stepping outside the familiar categories of space and time. Tunneling is a natural phenomenon, not a violation of physical law, but it shows how easily our intuitions mislead us. We expect particles to act like tiny stones or specks of dust, but instead they behave like waves capable of doing things that no classical object could. When we zoom in far enough, the solid world dissolves into something far stranger. A landscape of probabilities where barriers soften, rules bend, and movement takes on forms that defy imagination. And that is the quiet wonder of quantum tunneling. It's not just an anomaly, it's a glimpse into how deeply the universe hides complexity inside the ordinary, letting electrons disappear from one place and appear in another, as if distance were only a suggestion and time were far more flexible than it seems. If you fill a glass with water, everything about it seems predictable. The surface sits still. The liquid is quiet. You might even swirl it once or twice without expecting anything unusual to happen, but hidden inside that ordinary water is the potential for something extraordinary, something so strange that even today physicists still debate exactly how it works. It's called sonoluminescence, a phenomenon where tiny bubbles in a liquid collapse with such force that they emit flashes of light. Not gentle light, but light created under conditions so extreme that the temperature inside the bubble briefly rivals the surface of the sun. And all of this can happen in your kitchen sink. The first hints of sonoluminescence appeared around the 1930s when researchers studying underwater explosions noticed faint flashes during cavitation, the formation and collapse of bubbles. But no one understood what they were seeing. The equipment was crude, and the flashes were too fast to analyze. It wasn't until the late 1980s that scientists rediscovered the phenomenon under far more controlled conditions. The modern version works like this. Take a small container of water, inject a few microscopic gas bubbles, and use a powerful, precisely tuned sound wave to trap a bubble in the center of the liquid. The sound wave compresses and expands the bubble rhythmically, keeping it suspended in place. This setup is called a standing acoustic wave, and once the bubble stabilizes, something remarkable happens. During each compression cycle, the bubble collapses so quickly and to such a small size that a tiny flash of blue-white light appears. The flash lasts for less than a trillionth of a second, and the energy it releases is so concentrated that it defies easy explanation. It's one thing for sound to shake windows or vibrate a speaker cone. It's another for sound to create temperatures approaching tens of thousands of degrees Celsius, tens of thousands of degrees Fahrenheit. That leap from gentle acoustic pressure to intense heating is the heart of the mystery. Inside the bubble, the collapsing gas compresses to an extraordinary degree. As the bubble shrinks, it traps the gas molecules in a rapidly shrinking space. Pressures skyrocket, temperatures spike, The bubble walls accelerate inward at speeds faster than intuition allows. At the final moment of collapse, the bubble's diameter becomes so small that the energy stored inside has nowhere to go except outward in a sudden burst of radiation. For a tiny instant, the bubble becomes a microreactor, a point of extreme energy density contained within an everyday liquid. The flash of light is so faint that you need a dark room and sensitive photomultipliers to detect it. It doesn't illuminate the water, it doesn't glow visibly in your hand, but it is undeniable evidence that something profoundly energetic is happening inside the collapsing bubble. One of the most surprising features of sonoluminescence is its precision. The flashes can occur at the same point in the sound wave cycle with clockwork regularity, tens of thousands of times per second. This stability suggests that the bubble behaves almost like a resonant cavity, a tiny sphere whose oscillations synchronize perfectly with the sound field. In some experiments, a single bubble has been kept stable for hours, flashing with each cycle like the heartbeat of a microscopic star. Physicists began to ask deeper questions. How hot does the bubble get? How intense is the collapse? Can the internal conditions reach the point where nuclear fusion becomes possible? These questions emerged naturally because the temperatures inferred from experiments, sometimes tens of thousands of degrees Celsius, tens of thousands of degrees Fahrenheit, are similar to those inside stellar environments. The idea of tabletop fusion caused a brief scientific sensation in the 1990s. If a simple setup involving sound waves, water, and a trapped bubble could create conditions resembling those inside stars, maybe the bubble could fuse hydrogen atoms or deuterium. Early experiments claimed hints of neutron emissions, a signature of fusion, but these results proved difficult to reproduce, and later analyses suggested that the signals may have come from experimental noise or contamination. The consensus today is that while the bubble collapse does reach extreme conditions, it does not achieve sustained fusion. Still, the mere possibility, however fleeting, intrigued scientists around the world. Even setting fusion aside, the physics of sonoluminescence remains deeply puzzling. The process concentrates energy far more efficiently than expected. Sound waves carry relatively low energy, yet somehow that energy becomes compressed into a pinpoint of astonishing intensity. The bubble's final radius during collapse can be as small as a micron or less, meaning trillions of joules per cubic meter if extrapolated to larger scales. How does such extreme concentration occur so consistently in such an ordinary environment? There are multiple theories. Some physicists believe the bubble collapse generates shock waves that converge at the center, heating the gas far beyond typical compression. Others propose that the bubble becomes partially transparent to its own ultraviolet radiation, allowing thermal runaway. Some models suggest that the interior behaves like a plasma, an ionized gas, whose electrons and ions interact in ways that amplify the collapse, and a few theories even propose exotic mechanisms involving quantum effects, although these remain speculative. Despite decades of research, no single explanation fits all observations. Different liquids, different gases, different acoustic pressures. Each variation produces changes in the behavior that challenge existing models. Sonoluminescence sits at the intersection of fluid dynamics, thermodynamics, plasma physics, and quantum mechanics, and no single field fully captures what happens in the final instant of collapse. What makes this anomaly especially fascinating is that it occurs in everyday liquids. Water, glycerin, alcohol all can produce sonoluminescence under the right conditions. The liquid in your glass, the droplets in a sink, the bubbles rising in a boiling pot, all are governed by the same physics. They rarely collapse with enough precision to emit light, but the potential is always there. The phenomenon is a reminder that extraordinary behaviors can hide inside the most ordinary materials. It also illustrates something profound about energy concentration. In nature, energy tends to spread out. Heat flows from hot to cold. Waves dissipate. Motion slows, entropy rises, but in sonoluminescence, the opposite happens. Energy flows inward, not outward. Sound waves, which normally scatter and weaken, become focused into a shrinking cavity until the system achieves conditions that seem entirely out of scale with their source. It is as if the universe briefly forgets one of its usual habits, the habit of dispersing energy, and instead allows a moment of intense focus, a moment of collapse so precise that it produces light from sound. Sonoluminescence is not just a curiosity, it is a message hidden inside a bubble, that familiar substances can behave in ways that challenge our assumptions, that simple systems can create extreme conditions, and that even the most ordinary water can reveal glimpses of startling complexity when pushed to its limits. The flash may be brief, invisible to the naked eye, and confined to a microscopic space, but it carries with it the same lesson found throughout physics. Beneath the surface of everyday life, extraordinary things are always waiting to be discovered. If you've ever dripped a bit of water onto a very hot pan, you've seen a small miracle play out right in the kitchen. The drop doesn't sit still and evaporate, it doesn't hiss and vanish instantly. Instead, it pulls itself into a bead, lifts slightly off the surface, and begins to glide, zigzag, spin, or dart in unpredictable directions. It seems to dance, a tiny bright bead of liquid skating across a surface it shouldn't survive on. This strange behaviour is known as the Leidenfrost effect, and while it looks like a simple kitchen curiosity, it is actually a window into the deep physics of heat, motion, and chaos. The effect begins when a surface becomes much hotter than the boiling point of water, usually around 200 degrees Celsius, 392 degrees Fahrenheit, or higher. At these extreme temperatures, the bottom layer of the droplet vaporizes instantly the moment it touches the surface, but instead of boiling violently, the newly formed vapor creates a thin, insulating cushion between the droplet and the pan. This cushion keeps most of the water from contacting the surface directly. The drop levitates on its own vapor, protected by a layer only micrometers thick. The result is surprisingly stable in one sense. The droplet doesn't immediately evaporate. It lasts far longer than a droplet on a moderately hot surface, and yet wildly unstable in another, because the vapor cushion acts like a constantly shifting, self-generated hovercraft pad. The droplet isn't touching the pan. It is riding on a turbulent, high-speed layer of steam that forms, collapses, and reforms many times per second. That levitation is the key. It reduces friction almost to zero, allowing the droplet to slide effortlessly across the surface. If the pan is slightly tilted or uneven, the droplet travels up or down with surprising speed. Even subtle vibrations or imperfections on the metal can send it darting in unexpected directions. What looks like playful movement is actually the result of pressure variations inside the vapor film, tiny asymmetries. Differences in thickness, heat flow, or surface grain act like miniature engines, pushing the droplet along unpredictable trajectories. From above, the droplet often appears to skate or swirl as though following an invisible script. In reality, it is responding to chaotic microcurrents, temperature gradients, and shifting vapor channels forming beneath it. Physicists studying the Leidenfrost effect use high-speed cameras to track these motions, and even with precise measurements, predicting the droplet's path remains difficult. The motion can switch suddenly from slow drifting to rapid darting, from smooth rotation to abrupt jumps. That unpredictability is a hallmark of non-linear systems, systems where tiny changes lead to dramatically different outcomes. The thermodynamics behind the effect are equally unusual. Normally, when something hot touches something colder, heat transfers quickly and the cooler object warms up. But during the Leidenfrost effect, the thin vapor layer acts as a powerful insulator. Heat still flows, but at a slower rate than expected. Paradoxically, this means that a droplet on a very hot surface can last much longer than one on a surface closer to the boiling point. A droplet on a medium-hot pan will stick and sizzle violently, evaporating in seconds, but a droplet levitating on a superheated surface may glide around for far longer before finally shrinking away. This counterintuitive behavior mirrors a larger theme in physics. Extreme conditions sometimes create stability rather than chaos, and modest conditions sometimes destroy it. In the Leidenfrost regime, the droplet is safer when the surface is dangerously hot because the vapor layer forms more quickly and more evenly. At intermediate temperatures, where the vapor layer is unstable, the droplet rapidly breaks apart. Scientists have studied the phenomenon for centuries, but modern research has revealed deeper layers of complexity. The vapor layer beneath the droplet can exhibit miniature convection currents. These microflows push the droplet from one side to another, creating an ever-changing landscape of pressure zones. The droplet may spin, not because anything external is pushing it, but because uneven vapor production creates torque. In some setups, droplets can even climb up slopes against gravity when the vapor layer forms asymmetrically. There is a related behavior called the Leidenfrost ratchet, in which a patterned metal surface causes droplets to move in a specific direction without any external force. The grooves create asymmetrical vapor flow that pushes the droplets steadily to one side. This is one of those moments where the everyday and the exotic collide. A droplet on a kitchen pan can behave like a tiny self-propelled robot, driven entirely by temperature gradients and microscopic vapor dynamics. As researchers began exploring these effects more deeply, they uncovered additional layers of mystery. A Leidenfrost droplet can support oscillations, small rhythmic deformations of its surface. These oscillations correspond to different vibrational modes, like the harmonics of a musical instrument. The modes can merge, split, or transition unpredictably, resulting in complex motions that resemble the behavior of coupled oscillators in far more advanced physical systems. In some experiments, the droplet's internal motion becomes synchronized with the vibrations of the vapor layer, creating resonances that amplify its movement. These resonances can make droplets bounce, spin, or orbit one another. Two droplets placed near each other can interact in ways that mimic gravitational attraction or electrostatic repulsion, even though the forces at play are purely hydrodynamic. The kitchen becomes a stage for subtle multi-particle dynamics that echo much larger cosmic systems. What makes the Leidenfrost effect especially fascinating is how easily accessible it is. It doesn't require exotic materials or rare conditions. Any hot pan and a drop of water can reveal the same physics. It demonstrates that the boundary between everyday life and fundamental science is far thinner than we usually imagine. The pan on your stove can recreate behaviors found in advanced research on fluid dynamics, chaos theory, and nonlinear motion. It also shows how nature uses simple ingredients to produce complex results. A bit of water, a bit of heat, and the laws of thermodynamics combine to create something that looks almost alive. A droplet that moves with intention, avoids obstacles, and glides with surprising elegance. Of course, it isn't alive. But the complexity of its behavior is a reminder that motion doesn't need consciousness to appear purposeful. Patterns can emerge from physics alone. The Leidenfrost effect is a perfect example of chaotic behavior hiding in plain sight. It's a demonstration of how heat, motion, and fluid dynamics intertwine to produce results that defy intuition, and it's a glimpse of how deeply the world continues to surprise us, even in the most familiar places. The next time you heat a pan and watch a bead of water race across the surface, remember that beneath that simple movement lies a world of subtle interactions, a cushion of vapor acting like a levitating platform, turbulent flows shifting beneath the drop, and chaotic forces steering it across the landscape. It's a reminder that nature is always performing, even when we're just making breakfast. If you pick up your phone, hold a battery, or look at the circuitry inside a laptop, you are holding materials that behave in ways physicists still cannot fully explain. These materials are not rare, exotic, or restricted to giant laboratories. They are used in everyday electronics, in energy research, and in some of the most advanced experiments in condensed matter physics. They are called strange metals, and their defining behavior is so unexpected that it violates classical theories about how electrons should move inside solids. In most metals, copper, silver, aluminum, electrical resistance follows a predictable pattern. As the metal warms up, atoms vibrate more intensely. These vibrations act like obstacles, causing electrons to scatter. More heat means more scattering, and more scattering means higher resistance. The relationship is well defined and fits neatly into the equations of the standard model of solid-state physics. Strange metals do not follow this rule. Instead of showing resistance that grows with temperature in a curved, non-linear way, they show resistivity that increases perfectly linearly with temperature, double the resistance. Raise it again, and the resistance climbs with the same steady slope. No curvature, no deviation, no hint of saturation. Just a straight line, stretching sometimes from near absolute zero to extraordinarily high temperatures. This might seem like an unremarkable detail, but in physics, it is a startling anomaly. Classical theory simply does not allow electrons to behave this cleanly, this simply, or this strangely. In normal materials, there are limits to how often electrons can scatter. Once atoms vibrate enough, resistance should level off. In strange metals, the leveling never comes. It's as though the electrons are governed by a different set of rules entirely. Rules that ignore the careful architecture of decades of theoretical models. What makes this even more surprising is how common strange metals are becoming in modern technology. Certain copper oxides used in high-temperature superconductors behave like strange metals at temperatures above their superconducting transition. Some battery materials, especially those involving complex manganese or nickel oxides, also enter strange metal regimes. Components inside your phone or computer may rely on materials that flirt with strange metal behavior when driven hard enough. Something that once felt like a rare laboratory curiosity is slowly becoming part of everyday engineering, even though the underlying physics is still unresolved. To understand why strange metals are so baffling, it helps to recall how electrons behave in materials under normal conditions. In a typical metal, electrons move freely but not effortlessly. They scatter off vibrations, impurities, and other electrons. Theories like the Drude model or the more refined Fermi liquid theory describe this behavior effectively. These theories treat electrons like particles with well-defined properties: mass, energy, momentum. Even when electrons interact, the interactions are predictable and calculable. But strange metals do not behave like Fermi liquids. In fact, one of the defining features of a strange metal is that electrons act as though they have no well-defined identity. Their effective mass becomes ambiguous. Their scattering rate reaches the maximum allowed by the laws of physics, a limit called the Planckian time. At this limit, electrons scatter so frequently that they lose any sense of individuality. They become part of a collective state that behaves not like interacting particles, but like a fluid of entangled quantum objects. This is the heart of the anomaly. Strange metals sit at the boundary between the known and the unknown, a regime where quantum mechanics dominates so completely that classical pictures of electrons fall apart. Instead of moving like billiard balls bouncing off obstacles, electrons in strange metals behave like waves in a turbulent quantum sea. Their interactions are so strong, so intertwined, so correlated, that separating them into individual particles becomes impossible. This deeply quantum behavior is one reason strange metals are closely linked to superconductivity research. Many high-temperature superconductors begin as strange metals before transitioning to a superconducting state. When they are cooled, their chaotic electron motion suddenly becomes synchronized, forming Cooper pairs and allowing current to flow without resistance. It's as though the system undergoes an astonishing transformation, from a quantum turbulent metal to a perfectly ordered superconductor. Some physicists believe strange metals hold the key to understanding high-temperature superconductivity. one of the greatest unsolved problems in condensed matter physics. Classical theory can't explain why certain ceramics become superconducting at temperatures around -135 degrees Celsius, -211 degrees Fahrenheit. These temperatures are still cold, but far higher than traditional superconductors. Strange metal behavior sits right next to this transition, making researchers wonder if the two phenomena are deeply linked. More recently, strange metals have begun to fascinate theoretical physicists for an unexpected reason. They resemble systems described by ideas from quantum gravity and black hole physics. In particular, the way strange metals reach the Planckian limit mirrors how information is scrambled near black hole horizons. This doesn't mean strange metals contain miniature black holes, of course, but it hints that the mathematics governing these systems may draw from a shared underlying structure. It is rare for a material inside a battery or a chip to echo the physics of cosmic objects, but strange metals seem to bridge that gap. The linear resistivity of strange metals breaks classical theory because electrons shouldn't be able to scatter this frequently, and yet they do consistently across different materials and temperature ranges. This universality, the fact that so many unrelated compounds exhibit the same slope of linear resistivity, suggests that strange metals aren't accidents. They're revealing a fundamental state of matter that our current theories aren't equipped to describe. What makes this anomaly so compelling is that it sits inside materials we manufacture, manipulate, and rely on every day. Unlike black holes or particle colliders, strange metals appear inside devices small enough to fit in your hand. They demonstrate that some of the deepest mysteries in physics are not confined to the exotic. They arise in the circuitry of your phone, the electrodes of a battery, the crystals used in quantum computing research. They show up in laboratories not because they are rare, but because they are waiting, quietly, persistently, in the behavior of electrons packed tightly inside solids. Strange metals remind us that matter is far richer than our models allow, that the world of electrons is not always orderly or predictable, that even in systems we believe we understand, metals, oxides, semiconductors, there are regimes where the rules shift and the electrons behave as if they are part of a different universe entirely. And perhaps the most intriguing part is this: strange metals aren't a failure of theory. They are an invitation. They suggest that the familiar building blocks of matter still hold surprises, and that quantum behavior doesn't always hide beneath extremes. Sometimes it appears in the warmth of a circuit, the pulse of a battery, or the silent flow of current inside a device resting on your desk. They remind us that even in the everyday, the universe is still learning to reveal itself. Most of the time, sound feels gentle. You hear it, you feel it, but you rarely think of it as a physical force. It seems almost ghost-like, something that passes through air, touches your ears, vibrates your bones slightly, and moves on. But sound is much more than a sensory experience. It is pressure, motion, oscillation. It is the air itself being pushed and pulled in rapid waves. And under the right conditions, those waves can do something that feels like a magic trick. They can lift objects against gravity. This phenomenon, known as acoustic levitation, looks impossible when you first see it. A tiny bead, droplet, grain of dust, or even a small insect hovers in mid-air, motionless, held in place by nothing visible. There is no magnetism, no airflow, no trickery, just sound. A high-frequency speaker sends out pressure waves that form a standing wave, a pattern of fixed peaks and nulls, and at the right point in that pattern, an object can rest in equilibrium. It floats because the acoustic pressure pushing upward matches the force of gravity pulling downward. The air itself becomes a kind of invisible scaffold. When you see this in a laboratory, it breaks your intuition. We're used to gravity being absolute. Objects fall unless something stops them. A table, a magnet, a cushion of air, a jet of water. But in acoustic levitation, the stopping force is simply the oscillation of air particles, vibrating tens of thousands of times per second. Sound, normally so intangible, becomes architecture. The physics of this effect begins with the idea of standing waves. When a sound wave reflects between two surfaces, like a speaker and a reflector, The wave can overlap with itself. Some points vibrate strongly, others remain still. These still points are called nodes. At the nodes, pressure gradients form, creating regions where the force of the sound wave can trap small objects. The object settles into the node, where the upward acoustic force equals the downward pull of gravity. It doesn't rise or fall, it simply hovers. What makes this even more surprising is how gentle the system can be. In some experiments, researchers have levitated droplets of water, pieces of foam, and even delicate biological samples without touching them. NASA has studied acoustic levitation because it offers a way to handle materials without contamination. Pharmaceutical labs use it to suspend chemical droplets for analysis, keeping them free of container interference. Acoustic tweezers, devices that can move objects using sound alone, are being developed to manipulate cells in fluid chambers without mechanical force. These are advanced applications, but the underlying idea is something you can experience at home in a far simpler form. If you place a sheet of paper or a small piece of foil near a subwoofer as it plays a low-frequency tone, the vibration can lift or flutter it. If you run your finger gently through the air in front of your speakers, you sometimes feel pockets of stillness and intensity. Tiny variations in pressure caused by standing waves in the room. And although these home experiments aren't strong enough to levitate solid objects, they reveal the same pattern of alternating force that makes acoustic levitation possible. In fact, your bedroom or living room is full of standing waves. Whenever sound reflects off walls, floors, or ceilings, certain frequencies create resonant pockets where the wave's peaks and nulls align. You may have noticed that some notes sound louder in certain corners of a room, or that bass frequencies seem stronger in specific spots. That's because standing waves shape the way you perceive music. These sweet spots are pressure variations forming a pattern. The same physics that suspends droplets in a laboratory, just at a lower intensity. What makes acoustic levitation so compelling is how it challenges your sense of what sound can do. We know that sound can move large objects. Explosions, sonic booms, or powerful speakers can push air with enough force to rattle windows, but the idea that sound can hold an object, stabilizing it in equilibrium rather than blowing it away, feels counterintuitive. It reveals a subtlety we don't usually associate with pressure waves. At its core, acoustic levitation is a balance of forces. Gravity pulls down, acoustic pressure pushes up, and the air around the object shapes the stability. But beyond the mathematics, the effect exposes something deeper, the way our perception limits our understanding of everyday physics. To most people, sound is an experience, not a physical tool. We assume it cannot shape matter because we mostly interact with it passively. Yet the entire physical world responds to sound constantly. Bridges vibrate. Sand arranges into patterns on metal plates. Water forms ripples and peaks when exposed to certain frequencies. Even the human body, with its organs, cavities, and bones, resonates like an instrument. Acoustic levitation feels magical, not because the physics is mysterious, but because our intuition has trouble connecting something we hear to something we can see, lifting objects that disconnect between perception and reality is a reminder that the senses filter out more than they reveal. Sound waves are invisible, rapid, and subtle, so the fact that they can shape motion feels like a contradiction. There is another layer to this story, one that touches the boundary between physics and perception. The levitated object appears perfectly still, as though suspended in time, but the air beneath it is anything but calm. The system is dynamic, constantly adjusting, constantly vibrating. What looks like a stable, serene, floating object is actually caught in a storm of microscopic motion, held in a delicate balance. Our eyes see stillness because the movement is too small and too fast to perceive. The mind simplifies the complexity, presenting us with an illusion of stability where none exists. In a way, acoustic levitation is a metaphor for how perception works. We see solid objects, but at the atomic level they are mostly empty space. We see colours, but they are interpretations of light wavelengths. We hear sound, but to understand its force, we need instruments and equations. The levitating object feels like anti-gravity because our senses aren't equipped to detect the rapid oscillations doing the work. Even in advanced labs, researchers continue to uncover surprises about how sound shapes matter. Some experiments reveal that levitated droplets can spin or deform in unexpected ways. Others show that objects can be moved along prescribed paths, pushed or pulled by carefully tuned acoustic fields. A few studies even explore whether sound can assemble structures, tiny particles forming patterns as they respond to pressure nodes. The more we look, the more we find that sound is not just a medium for communication, but a powerful sculptor of matter. Acoustic levitation sits at a fascinating intersection. It is a very old physical phenomenon, pressure waves interacting with objects, and yet it feels like a glimpse into the future. It demonstrates that even everyday forces, when arranged precisely, can produce behaviours that seem to defy intuition. It invites us to reconsider the boundaries between perception and physics, and it reminds us that the world is filled with forces we do not usually notice, shaping matter quietly, invisibly, all around us. In the end, the illusion of anti-gravity is not an illusion at all. It is simply physics revealing itself in a way that feels unfamiliar to our senses, turning sound, something we listen to, into something that can lift, hold, and move the world. There is a quiet assumption woven into everyday life that we can measure the world without disturbing it. We take temperatures, check pressures, weigh objects, test materials, and monitor systems with the confidence that our instruments simply reveal what is already there. But in reality, every act of measurement alters the thing being measured. Sometimes the effect is so small that it goes unnoticed. Sometimes it is significant enough to change the result entirely, and sometimes it unveils something deeper. The idea that the boundary between observer and observed is never as clean as we imagine. The observer effect is often associated with quantum mechanics, where the act of measurement unavoidably disturbs a particle's state. But this principle extends far beyond the quantum world. It shows up in the simplest corners of everyday life, in tools we take for granted, in actions we repeat without thinking. You encounter it not only when you measure electrons, but also when you measure tire pressure, take your temperature, or check the battery in a device. Take something as ordinary as measuring heat. A laser thermometer gives one reading. A contact thermometer gives another. The numbers differ not because the surface is changing rapidly, but because each measurement method interacts with the environment differently. A laser thermometer infers temperature from infrared radiation emitted by the surface. It is fast and clean, but only measures the topmost layer. A contact thermometer actually draws heat into itself, equalizing with what it touches, and in doing so, changes the temperature it is trying to measure. It absorbs energy and alters the system. This is not an error. It is the consequence of interacting with reality. You can't dip a thermometer into water without cooling or heating a tiny region around it. You can't weigh something without placing it on a scale. You can't check body temperature without exchanging heat. Every measurement is a negotiation between the system and the tool, a dialogue rather than a passive observation. The effect becomes even more obvious in something as mundane as checking tire pressure. When you press a gauge onto a tire valve, a small amount of air escapes into the gauge. That tiny release slightly reduces the pressure you're trying to measure. The act of checking the pressure alters it. In many cases, the difference is trivial, but in precision work, it matters. Pilots checking aircraft tires must account for it. Engineers working with sealed systems must account for it. Even home mechanics sometimes notice that repeated checks yield slightly lower readings, not because the tire is leaking, but because each measurement drains a minuscule amount of air. Similarly, when measuring blood pressure, simply placing a cuff around the arm can stimulate the nervous system, enough that readings may vary depending on whether the person feels calm or anxious. Measuring blood sugar requires drawing blood, which has its own minor physiological effects. And in laboratory experiments, taking a sample from a chemical system can remove key reactants, subtly altering future measurements. All these examples highlight a simple truth. Measurement is intervention, but there is another layer, a more subtle one, which begins when we consider how the act of observing influences human behavior. The Hawthorne effect, for example, describes how people change their actions when they know they are being monitored. Workers increase productivity. Students adjust their study patterns. Drivers behave better when they notice speed cameras. Observation shapes outcomes, not because of physical disturbance, but because knowing changes doing. This may seem unrelated to physics, yet it mirrors the same principle. The observer is part of the system. Even animals exhibit observer effects. A thermometer placed in a terrarium changes the humidity. A wildlife camera alters predator behavior. Even the presence of a researcher can influence the movements of the species being studied. This is not quantum. It is simply the nature of interaction. And when we return to physics itself, the observer effect becomes even more interesting. In classical systems, the disturbance may be small or negligible, but in quantum systems, it is unavoidable. Electrons don't have precise positions and momenta until measured. Photons behave differently, depending on whether or not they are watched. At small enough scales, the universe refuses to let you peek without participating. A measurement is not a window, it is a handshake. This leads to a deeper philosophical question. What does it mean for the universe to respond to observation? Not in the mystical sense, but in the practical, measurable one. When you measure something, you are exchanging energy, momentum, or information with it. You are touching it with photons, electrons, pressure, or heat. You are making yourself part of the process. Even perception is a form of measurement. The light entering your eyes bounces off surfaces, changing those surfaces on the microscopic scale. The sound waves entering your ears lose energy as they vibrate your eardrum. Smelling something pulls molecules into your nose, altering the distribution in the air. Seeing, hearing, touching, tasting, all of them participate in the world, not simply observe it. In this sense, the universe is never entirely separate from the mind that perceives it. Observation becomes interaction. Interaction becomes influence. Influence becomes change. And change becomes part of the system. This is why the observer effect sits so naturally in the final chapter of this episode. It touches every form of anomaly we've explored. The quantum behaviors that change when watched, the biological systems that respond to attention, the fluids and materials whose properties shift when measured. It reveals something quiet but profound, that knowing the world is never passive. To know is to participate. When a scientist peers into a microscope, the act of illumination shapes the sample. When a sound wave levitates an object, the measurement of its position alters the field sustaining it. When a small bubble collapses in sonoluminescence, the tools we use to detect the flash change the temperature of the liquid. When water freezes faster or slower depending on how we set up the experiment, our method becomes part of the story. And when a human looks out at the world, their state of mind, expectations, and attention influence how the world appears, how it is interpreted, and even how the body responds. The observer effect, in the end, is not just a rule of physics. It is a reminder of connectedness. A reminder that the universe does not stand still while we measure it. It shifts, adapts, responds, and sometimes hides or reveals depending on how we choose to look. It is the universe noticing that we are noticing, and in that subtle recognition, in that interplay between consciousness and the physical world, lies one of the deepest everyday anomalies of all. As we reach the end of this quiet journey through everyday anomalies, let your mind settle for a moment in the space between curiosity and calm. The world around you is full of mysteries hiding in plain sight, in water, in light, in sound, in simple acts of observation. These small strangenesses remind us that reality is never finished, always waiting to be rediscovered. If you've enjoyed wandering through these quiet wonders, consider subscribing and leaving a comment about where you're listening from tonight. Until next time, rest well, stay curious, and let the world surprise you gently.